Geothermal energy is a form of renewable energy that is available around the clock, irrespective of weather, climate, and daylight. It comprises usable heat from the Earth's interior, and it has long been associated with hot springs and hydrothermal activity. My name is Stuart Simmons, and I'm one of the geoscientists working on the Utah Forge project. This webinar builds on an earlier one covering conventional geothermal resources, and it focuses on their surface expression, including hot springs, steaming ground, and related thermal features. These are the products of hydrothermal circulation beneath the surface, and they are often found in the vicinity of volcanic centers, fault belts, and mountainous regions. There are three main points to cover. First, elaborate the different types of surface thermal manifestations. 2. Show how these relate to shallow hydrology and deep hydrothermal fluid flow. And lastly, provide an understanding of natural and induced temporal variation or evolution. Before diving in, let's review a few salient points about geothermal resources. First, the Earth is a huge thermal battery with vast energy resources, and heat is being continuously generated by radioactive decay of elements such as uranium, thorium, and potassium in the Earth's interior. Heat transfer occurs by conduction and convection, and geology dictates how and where geothermal energy can be utilized. The hottest geothermal resources are used to generate electricity based on production of steam and/or hot water from deep production wells. Cooler geothermal resources are used for a wide range of direct use applications. The surface expression of such resources includes hot springs, fumaroles, and steam vents. Second, the global distribution of conventional geothermal resources is limited by favorable geological conditions, and I probably can't emphasize this enough. The legend shows that they are divided into various types. The highest grade resources are shown as the red-filled circles, and they are associated with volcanic centers and/or young magmatic intrusions. They are localized along plate boundaries. The ones marked by gray-filled circles tend to be lower grade, but still important for geothermal energy production and are associated with extensional fault systems. Prominent examples occur across the basin and range of the western USA as well as western Turkey. The last type of geothermal resource occurs in hot sedimentary basins, which are widespread but underdeveloped. The only ones currently used for geothermal energy production are found in China and across Europe. Third, high-grade resources occur in geologically dynamic settings as shown in this set of photos from the North Island of New Zealand. Although generally associated with geologic hazards, magmatic heat and tectonic fracturing have beneficial effects in terms of stimulating and sustaining hydrothermal circulation which hosts productive geothermal resources. Fourth, in respect to developing a geothermal resource, surface features, particularly hot springs, are some of the first to be mapped, sampled, and interpreted by geoscientists. Such data and information are useful for determining the potential size and grade of the resource under investigation, and they precede expensive but essential investment in geophysical surveys, well drilling, and production testing. Thus, assessment of hot springs provides a means by which prospects can be assessed and ranked. And lastly, the geothermal gradient is a key attribute of different types and grades of geothermal resources. The geothermal gradient represents the change in temperature with depth, and conductive gradients are different from convective gradients. That's because conduction and convection are two different types of heat transfer in the shallow crust. For example, most areas, including the ground directly beneath your feet, have a thermal gradient of between 10 and 40 degrees C per kilometer. The one for 25 degrees C per kilometer is plotted as a straight blue line. It represents a global average, and it is characterized by steadily increasing temperature with increasing depth, represented by a constant slope. Such a linear trend is characteristic of conductive heat transfer through solid rock. Furthermore, the surface expression is unremarkable, absent of any sort of thermal activity, anomalous thermal ground, and instead is simply represented by cold ground. Only in a few places do thermal gradients exceed the normal conductive trend, and such occurrences are the products of hydrothermal convection. In these locations, thermal energy is transported or transferred to the surface by the flow of hot fluids. For such convective heat transfer, the maximum thermal gradient is represented by the red line designated boiling point curve. Everywhere along this line, hot water is just at boiling condition. Convective gradients develop locally in tectonically and volcanically active regions. Strictly, a convective thermal gradient is perfectly vertical, as buoyant hot water transfers heat to the surface. Such a condition would be expected for a mature, long-lived vertical flow path, wherein the temperature of the hot water is the same as the rock along the flow path. Once the convective upflow intersects the boiling point for depth condition, the temperature of the rising fluid decreases as steam is produced from the depressurizing water. Remember, the boiling point for depth curve is the maximum temperature as a function of depth attainable in the shallow crust, except for rare transient excursions, such as when a volcano is actively erupting. To put the process of convective heat transfer into context, this schematic diagram shows the movement of fluid related to deep magmatic intrusion in volcanic belts. The magma has a temperature of 800 degrees C or hotter. As it cools, it releases thermal energy which heats local pore waters that makes them buoyant, inducing development of a convection cell as represented by the blue and red arrows. A plume of hot water results, transferring magmatic heat through to the surface. The circulation depths of convection cells are difficult to measure, but conceptually they may extend to greater than 5 kilometers beneath the surface. The hot springs and other thermal features form over both the upflow and outflow zones as represented by the lavender-filled circles, and they represent the highest level effects of hydrothermal heat and mass transfer in the crust. Surface thermal features occur in a diversity of geological settings, including hot sedimentary basins, extensional fault belts, as well as centers of magmatic and volcanic activity. The latter two types are associated with convective heat transfer and hydrothermal circulation, whereas in hot sedimentary basins, thermal waters are stored in hot aquifers and can only leak out at the surface if there are pathways, for example along permeable fault structures. Turning now to the classification of surface features, some are based on fluid chemistry and others are based on discharge and heat flow characteristics. For our purpose, a hydrological framework is utilized to provide a basic understanding of their origins and differences. To start, hot springs encompass the spectrum of surface features occurring at the water table. They discharge clear chloride-rich or bicarbonate-rich waters at temperatures that range from boiling down to subboiling of less than 50 degrees Celsius. Flow rates are commonly on the order of 0.5 to 5 liters per second, but in rare cases they can attain and exceed 100 liters per second. Evaporation is an important mechanism of mass transfer that is often difficult to quantify even if it is significant in terms of heat loss. Geysers are a rare type of hot spring that discharge discontinuously, fountaining boiling hot water and steam. Hot springs are typically surrounded by chemical deposits made of silica sinter or travertine. The former is primarily composed of amorphous silica, whereas the latter is made of calcium carbonate. These products are the geological fingerprints of superficial hydrothermal activity. Steam discharges include fumaroles, steam vents, mud pots, and steaming ground. These occur above the water table, sometimes by less than a few meters. They are associated with hot, barren ground, stunted vegetation, as well as acid alteration and rock dissolution, which make the ground soft and hazardous to walk over. Steam discharge is generally difficult to quantify, especially where diffuse, but it can be vigorous and audible, as in the case of an energetic fumarole. Cold gas seeps, also known as maffeti in Italy or kaipohan in the Philippines, are another distinctive type of thermal feature, even if the discharge is made of cold gas, predominantly carbon dioxide. These also form mainly above the water table, and they are visible where gas bubbles through shallow pools. Otherwise, they are rather subtle and noticeable as areas devoid of vegetation. Thus, in densely vegetated areas, they are quite striking as the carbon dioxide flux kills the roots of growing plants, forming clearings that have nice sharp boundaries and other characteristics that include sporadic deposits of pale yellow native sulfur, bleached ground, and dead animals, as the carbon dioxide will pond in depressions, displacing air. These features form high above the boiling water table, separated by distances of greater than 100 meters, for example in steep terrain, or where gas fluxes are anomalously high, but geological conditions impede the ascent of hot water. Here, the three different types of surface thermal features are shown in shallow hydrologic context in cross-sectional view. The continuous black line represents the surface and slopes downward to the right into a lake-filled depression. The dashed line represents the hydrothermal water table that separates the vadose zone from the phreatic zone. In the phreatic zone, all pore space is filled with hot liquid water and sometimes a small fraction of steam and gas, whereas in the vadose zone, the pore space is mainly filled with gas, including steam and geothermal gases rising from the water table. The rising plume of boiling to near boiling hot water is shown in yellow. Overall, the water table represents a critical divide that controls the occurrences of the three types of surface features. So now let's look at some examples of surface features occurring in the North Island of New Zealand. We start with a small boiling hot spring about 0.5 meters in diameter, ringed by a deposit of silica sinter. The outflow discharges through the channel going away from the viewer at about 0.5 to 1 liters per second. Importantly, the surface of the pool represents the hydrothermal water table. In other words, the surface of the pool is the piezometric surface of the hydropressured regime that controls the hydrology of the underlying hot water plume supplying the hot springs. The diffuse discharge of steam makes up the steaming ground shown in this photo. It forms above the boiling water table and represents a distributed style of heat and mass transfer that contrasts with the point discharge of a hot spring or steam vent. In this photo, you can see both boiling hot springs and steaming ground side by side, illustrating the separation in type of surface activity above and at the water table. The large pool in the middle ground is filled with clear, chloride-rich water, and it is surrounded by a thick deposit of silica sinter. A second boiling hot spring occurs to the right on the lower flanks of the mostly barren slope. The lavender circles mark the highest levels of water discharge and the hydrothermal water table. Upslope, the ground is soft, hot, and steaming, and a treacherous surface to walk over. The inset shows a cross-sectional view of the relationship between the different styles of surface expression and the hydrothermal water table. Here, zooming out gives you a broader context. Many other hot springs dot the silica-sintered covered terraces which step down to the lake level. From this, you can see how a large sinter sheet can form from the overflow of multiple hot springs. Additionally, the water levels of these various hot springs can change over very short distances. Returning to steam discharges, other related features include mud pots, which in contrast to the clear hot springs, are made of acidic water having a thick suspension of clays and sulfur-bearing minerals. These are alteration products of volcanic rocks, and they have been transformed by reaction with acidic steam-heated water. The corrosive effect of these acidic waters is shown here, where a boiling mud pot occupies the floor of a collapse crater and is situated beneath an arch-like structure that is formed by dissolution of the volcanic country rock. This mud pot is no more than a few meters above the water table. The third type of surface feature comprises cold gas seeps. In the foreground, carbon dioxide bubbles through a pool of cold water, while a large log and small clearing behind it represent a cold gas seep. Here, another cold gas seep is represented by the clearing in densely vegetated bush, and it comes with pale yellow deposits of native sulfur. These surface features form mainly above the water table, sometimes by several hundred meters. Switching gears, let's now look at how hot springs relate to underlying geothermal resources. This is an aerial photograph of the Oahu field in New Zealand. The light-colored rectangles represent well pads which are connected by pipelines that transmit steam to the power station next to the tall cooling tower which is emitting a steam plume. When originally explored in the 1960s, before any wells were drilled, there was but one prominent natural surface feature in the form of the Oahu Pool, shown in the inset. It is located in the northwest part of the field, and the photo shows what it looked like in 1987. It naturally discharged a near-boiling chloride bicarbonate water at a rate of about 10 liters per second. Here, the field is represented in two map views on the left. In A, the locations of natural surface activity and thermal ground are shown. Their extent is modest and localized primarily in the vicinity of the Oahu Pool. In B, the drilling of deep vertical wells proved the existence of the high-grade resource outlined in yellow, which had a reservoir temperature in excess of 250 degrees Celsius. In C, a cross-section view of the hydrothermal system, the geothermal reservoir, and the vertical wells are portrayed. An important point is that the extent of surface thermal activity can be deceptive and underrepresent the extent of the underlying resource. Separately, the natural flow of the Oahu Pool changed once production began in the late 1980s in response to an induced pressure drop and a sharp lowering of the spring water level. Since then, it has been refilled and rehabilitated through an engineered supply of hot water. An important conclusion is that water levels in hot springs are sensitive to changes in the water table, particularly where production induces a pressure drop. The history of exploitation at Rotorua is a good example. Rotorua is a major urban center with a population of over 50,000 inhabitants. The city is built on top of a high-temperature geothermal system, and the city is dotted by more than 1,500 hot springs and related surface features. One of the most important hot springs is the Pohutu Geyser, which is erupting in the foreground, and the hot spring activity across the city supports a vibrant tourism industry. Geothermal energy has also long been used for domestic and commercial heating in the city, utilizing hot water produced from relatively shallow wells. In the mid-1980s, and in response to decline in geyser behavior, all wells within 1.5 kilometers of Pohutu were closed. Since then, there has been regulated control on geothermal production to preserve the natural surface thermal activity. The result has been recovery and restoration of these much valued features, and management of subsurface pressure has proven to be a useful tool in mitigating change. Geothermal exploitation can sometimes influence and cause change in surface thermal activity, but hot springs and related features also evolve naturally over time. An analogy is drawn here with atmospheric convection that produces billowing cumulonimbus clouds and towering thunderheads. Like hydrothermal convection cells, they develop and dissipate, but over short periods of time of just a few hours. In comparison, and although difficult to measure and date, hydrothermal activity is believed to last for thousands to tens of thousands of years. Within that time frame, hot spring flows and water levels are subject to short-term changes for reasons that are difficult to resolve. Just like for Rotorua and Ohaki, changes in pressure are a causative agent. Returning to Oraki Korako, the water level in the central spring on the upper terrace is generally completely filled, overflowing with hot boiling water, as was shown earlier. But sometimes, the water level drops and the spring dries out. Such a condition happens naturally and periodically with no obvious cause. Over time, the hot spring eventually refills to its previous flowing state. Although changes in water levels of springs have been documented, a full understanding of the regulating controls on their behavior and surface discharge remain unresolved. In yet another example, at the Waitapu field, the breaking up of a silica sinter sheet, which formed from a once active boiling geysering hot spring, marks the previous level of the water table, which subsequently lowered in response to a natural evolution in the hydrology of the system. Note this system is still quite active and one of the largest in the central topovolcanic zone. So far, we have seen examples of surface thermal activities associated with geothermal resources occurring in the North Island of New Zealand, and the various fields are located in the two maps on the left. Now let's shift the focus to the Basin and Range province in the western USA and the occurrences of surface thermal activity in southwestern Utah. The map view provides a close-up and shows the location of scattered hot springs across the Sevier and Escalante deserts in southwestern Utah. These springs discharge clear chloride bicarbonate-rich water between 35 and 80 degrees Celsius. The map also shows the locations of 3 geothermal production fields, the hottest of which is Roosevelt Hot Springs. Cove Fort and Thermo are cooler, producing 25 and 10 megawatts of electrical power, respectively. Within about 1.5 kilometers of the thermal production field, the Thermo hot spring discharges at 85 degrees C and it shows no sign of induced change in flow or temperature over the last 10 years of intermittent monitoring. COFORT is an interesting field having a resource temperature of about 170 degrees and covering a large area extending 10 kilometers north to south. In the 1990s, a shallow steam-filled reservoir was exploited near Sulphurdale, indicating subsurface boiling. But with the subsequent drilling of deeper wells, hot water is now currently produced to generate electricity. Surface thermal activity is absent except for scattered occurrences of bleached rock devoid of vegetation. These are cold gas seeps as confirmed by soil gas surveys, and decades ago they were prospected as a source for native sulfur. Nonetheless, the field is rather extensive and the resource shows potential for further development. The map view on the left shows the location of the power station in the southern part of the COFORT field and the location of cold gas seeps in the northern part of the field. The power plant and cold gas seeps are separated by a distance of several kilometers. A close-up on the right shows the cold seep in the northwest, and the bleached ground is clearly visible in this Google Earth image. When commissioned in 1984, Roosevelt Hot Springs was one of the hottest known resources in the Basin and Range Province, with a reservoir temperature of 260 degrees Celsius, and it currently produces 38 megawatts total from flash and binary plants. An aerial view of the setting is shown looking south along the range front of the Mineral Mountains. There are 4 production wells situated east of the Opal Mound Fault, which extends about 7 kilometers in a north-south direction. An extinct surface feature occurs at the south end of the structure at Opal Mound. At the north end, steaming ground is locally developed in response to lowering of the water table induced by production. At Opal Mound, at the south end of the Opal Mound Fault, a thick silica sinter sheet is exposed, and radiocarbon dating indicates that it is about 2,000 years old. In this view, you can see the laminated silica sinter on either side of the fissure that was the feeder vent for the surface discharge of hot boiling water. The spring died naturally in prehistoric time, even though it overlies a zone of hot boiling upflow today. In the northern part of the field, steaming ground is locally developed as a direct response to geothermal production, which, as mentioned, started in 1984. The lowering of the water table expanded the vadose zone and increased the steam flow to the surface, killing the vegetation. The amount of water table lowering is about 300 meters, as seen in the graphic, which shows the change in the hydrology in response to geothermal production. The expansion of the vadose zone in response to depressurization had the biggest effect on surface thermal activity, but this only occurred locally and in spite of reinjection. A similar magnitude effect of depressurization occurred in the Wairākei geothermal field in New Zealand, and it was decades before reinjection was used to dispose of wastewater. The result was formation of a large area of steaming ground called Craters of the Moon, and today this area is visited by numerous tourists annually, whereas the remote, isolated location of Roosevelt Hot Springs means that the site is rarely visited. A key takeaway is that changes in surface thermal activity are largely the result of changes in the water table. Increasingly, new geothermal developments are deploying effective injection strategies that minimize the production of effects, but controlling pressure to sustain natural hot spring activity. To summarize, hot springs, steam vents, and related thermal features are the surface expression of deep circulation of hot water in hydrothermal systems that host geothermal resources in a diversity of geological settings. Surface thermal features reflect the transfer of deep geothermal energy and shallow hydrology. Moreover, the extent of surface thermal activity can be deceptive and underrepresent the extent of the underlying resource. The type and behavior of surface features are controlled by their relation to the water table and the mass flow of rising hot hydrothermal fluid. Hot springs form at the water table and discharge clear chloride or bicarbonate-rich water. They are often surrounded by chemical deposits of silica sinter or travertine made of calcium carbonate. Steam discharges form above the water table, and these include fumaroles, mudpots, and steaming ground, which are associated with hot, barren ground and stunted vegetation, as well as acid alteration and rock dissolution that make the ground soft and hazardous to walk over. Cold gas seeps also occur above the water table. They discharge primarily carbon dioxide, which is invisible, and form patches that are barren of vegetation that have sporadic deposits of native sulfur and that are characterized by bubbling pools and or bleached ground. Surface features evolve naturally, and they also respond to pressure changes induced by geothermal production, resulting in a lowering and rising of water levels. Lastly, in production fields, pressure support through a combination of injection and monitoring can help to sustain natural hot spring activity. Thanks for watching, and if you are interested in more information about geothermal technologies and Utah Forge, please visit our website. This presentation is sponsored by the U.S. Department of Energy.